And the first speaker is Dov Sagi from the Weizmann Institute, Plasticity of Visual Perception, Learning and Adaptation. And the speakers, please limit yourself to 20 minutes. I'll sign to you 2 minutes before the end of the talk.
Okay, so first, Mazal Tov to Uri. This is a great achievement. I think I know Uri almost 30 years. Maybe.
Don't say that.
Yeah, I think that's the first time I met him. He visited me interested in psychophysics. I think that was the first time I heard about amblyopia. Almost sure that I never heard about it before. And he had some kind of strange ideas, which we followed on. And I must say that I had really many years and many collaboration with Uri, very exciting, kind of very creative and very exciting collaboration. So some of my thoughts today, scientific thoughts, are definitely motivated by the work with Uri. So today, and of course, congratulations to Bar-Ilan, Mazal Tov, for having Uri and the optometry school. So what I want to speak today is about perceptual learning. Then he started describing some work on perceptual learning and gave a nice introduction. So I will follow on and we'll speak about perceptual learning and sensory adaptation, how the two interact and the outcome of this interaction between the ongoing sensory adaptation and perceptual learning. So this is another introductory slide for perceptual learning. What we mean by perceptual learning is that performance, usually threshold on some task, visual task, or visual learning, improve with practice, and that can be anything, acuity or phase discrimination, motion discrimination, gabor detection in noise, face, this was phase and this is face detection. Once you let the subject practice on this task of identification, detecting face in noise, they just improve with time. I mean, there is nothing to do, that happens automatically without any instruction. They just do better and threshold improves from day to day. So these are kind of typical learning curves. You start day one with high threshold, whatever this dimension is. Next day you're doing much better, and within 3-4 days you converge to a much better performance level. Some learning are slower, some are faster, but this is kind of typical. Now, perceptual learning has some basic features. One, it stays forever. You practice on this task, it's kind of difficult. You run many trials, but after a few days you get there, and now if you test the subject again, we don't have results here, but if you bring back the subject to the lab after 2-3 years, you get the same threshold, practically the same threshold. So this is kind of procedural or skill learning, like learning to run or swim or riding a bicycle. But it has some limitations, and the main limitation of perceptual learning is specificity. The problem is that you improve on the task you perform. So let's say you practice this task where the two gratings are aligned in a different way, in different phase combinations. You improve on this task. Once you move the target to a different spatial location in the visual field, you lose the learning. Once you change spatial frequency, orientation, here they're oriented vertically. Let's say now you give the subject the same task, but horizontally. The gratings are horizontal, so he has to learn. Again, this is an example for location specificity. So here subject, this is a texture discrimination task, learned in one location, this quadrant of the visual field. After that, the target was moved to this quadrant, and they have to relearn the task. So this is a major limitation of perceptual learning. Definitely, if you think about the practical application, like training amblyopes or whatever kind of visual rehabilitation, you want to have some kind of more generalized training schedule and eliminate this specificity. So our suspect is sensory adaptation, and the point is that learning involves continuous exploration and repeated exposure. I mean, there are many days there, many trials. Every session can be a few hundred trials, maybe 300, 400, 800, depending on on the lab and things like that. Now, when you repeat a stimulus many times or you expose a subject for a long time for the same stimulus, you get sensory adaptation. We're all familiar with sensory adaptation, retinal adaptation for mean intensity, color adaptation, but there are also higher level adaptation to gratings and orientation. And this is not only a problem of vision, it can be any other sense, or I may say even general in life. If you adapt to society, to a specific behavior, then it will be more difficult, or you will have a different type of learning when you try to identify specific behavior after you adapt to this behavior. So what I mean by adaptation in the context of this talk is orientation-specific sensitivity reduction. And this goes back many years, maybe 50, 60 years, the work of Fergus Campbell and Blakemore, Colin Blakemore. You are exposed to this type of gratings, and after a few minutes you test sensitivity. And okay, and this is the contrast sensitivity function, human subject, Fergus Campbell here. And this is before adaptation, and after adaptation we get this reduction of sensitivity around the adapted frequency. This is a spatial frequency specific adaptation. And from this pattern of results you can compute some kind of filter or bandwidth of adaptation, which is specific again to orientation and spatial frequency. And you get the famous tilt after effect, which we can demonstrate here. What you need to do, fixate your eye here, move the eye left and right, and then for a few seconds, and then fixate here, and these two vertical gratings should be seen tilted. So you just do that, and now move here. And this is a classical kind of tilt after effect. So the explanation, you adapt to this orientation, these filters, these orientation selective units become less sensitive, so all your orientation estimation is biased now away from it, and the vertical is seen away from this one, and this vertical is seen away from this one. So we use this tilt after effect to estimate adaptation during perceptual learning. So the main actors in the game are adaptation, online local adjustment to changing stimulation, which is a short-term process because it's believed to go away after a few minutes. You re-adapt because you constantly adapt to the condition of the environment. So if you change light, you adapt to the new light. Learning, improved classification of input patterns. So it's more like learning to discriminate between things. And this is long term. As I mentioned, it stays for years. So you learn to identify a specific face. Now you know to identify this face, and you can keep it forever. So the main point is that during training, local adaptation modifies early representation, interferes with learning, and possibly leading to specificity of learning. Okay. So the experimental paradigm we use is the texture discrimination task. In this task, there is a target. It's difficult to see from here. There is a target here. The three lines, which are here, are aligned horizontally. In half of the tiles are aligned vertically, and subject need to identify the global orientation of these lines, vertical, horizontal. This is presented for a short time. This particular experiment is 40 milliseconds, and then followed by mask, and we measure the stimulus on center synchrony, the time between the target and the mask, as a measure of performance. We use it as a measure of performance. The faster, the shorter the SOA is. I mean, subject that can perform a shorter SOA do better. Initially, you need longer SOAs. So this is an example of a trial. So as you see, initially it is very difficult. I'm going backward now, because this is fast. But after a few days, I mean, it becomes very easy. I mean, this is the magic of perceptual learning. So what we see here is, again, learning curve, but we see in addition here we see the threshold, the stimulus on center synchrony threshold. Initially, they are higher. After 5 days of practice, they get lower. But at the same time, we can see, because we have 800 tiles here within each session, that within a session, thresholds get higher. Actually, they get worse within. So we start here the first day. At the end of the day, we are here. Next day, we are better. But we end up here. At the end, we see very strong adaptation. We see learning. So initially, you perform better, and then you adapt. So to verify that this is really adaptation and not just fatigue, the subject get tired during performing the session, we measure tilt after effect at different location in the stimulus. So this is a tilt after effect, the bias in orientation of perceived vertical as a function of location for 4 different specific locations in the stimulus. So the strong tilt after effect we see in locations that correspond to the target, to the center element of the target. So these locations, which are extensively exposed to this tilted line, get a very strong tilt after effect, meaning there is adaptation. On the other hand, on the other side, we see locations that are in the background. These 2 locations with minimal tilt after effect, non-significant tilt after effect, actually are locations in the background. One is a far background, and one is a very close background. So we see also that there is a very big difference in the effect of adaptation in location belonging to the target and location belonging to the background. And maybe the most interesting location is this location corresponding to the side of the target, to this element. Because the target is switching orientation all the time, this location is exposed half of the time to target element, half of the time to background element. So on the average, you do not expect tilt after effect because these 2 orientations, the background and the target, are balanced. One takes you to one way, the other takes you to another way, but still you get a strong tilt after effect, significant tilt after effect, as if you adapt to the target orientation. So this is very strange. I mean, this is a very interesting result in the context of adaptation, which is believed to be sensory and passive ongoing process of adaptation, because it shows that it's strongly dependent on the task, on the target location, etc. So one of the outcomes of this experiment is that adaptation, sensory adaptation, that leading to this type of orientation-specific adaptation, is not a simple local process that depends on the activity of local orientation selective unit, but it incorporates some kind of context effect, maybe because of the task, because we attend to the task, we need to identify the task, maybe because of the stimulus configuration. But the interesting thing is that you get bias toward the target. Another interesting thing about adaptation is that you improve with practice. We measured the tilt after effect twice after each session. And we look at the effect of days. So the first time, immediately after that, that's the target lateral location. This target a change that on the side of this triplet. So the first measurement immediately after the adaptation does not change much with days. It's not experience dependent. But the second measurement immediately after that, let's say 5 minutes or so, changes with days. So initially there is no tilt after effect, but at the end of day 5, there is a tilt after effect at the second measurement. So this means that the tilt after effect actually increasing in persistence. You get longer tilt after effect. So that's another feature of sensory adaptation now, that it changes with practice. It's not only task dependent, it also seems to be plastic in the sense that it extends, it stays for a longer time with practice. And this change correlates actually with the deterioration, right? Because we can see that you get more deterioration here, more effect on performance here than here, and this correlates with the persistence of the tilt after effect. So standard tilt after effect location consistently stimulated by the target, to find that. Tilt after effect is it reduced, is location stimulated by both targets and background orientation, and increased with training, and no tilt after effect background. So there are highly local shape deformation of individual textile. So the next question we asked whether this accounts for specificity. So maybe because of these local specific adaptive changes, the target location, what we learn is very specific to this adapted situation, and we cannot generalize it to a different location that did not go through the same adaptation. And we see that adaptation has some long-term effect. So with Hila Harris, both the previous work also was done with Hila Harris. We asked whether learning can be generalized once adaptation is reduced. So what we did, we generated condition known to reduce the orientation-dependent adaptation, and this is by mixing different orientation. So it's known in the literature that if you mix two orientations differing by 45 degrees, you can reduce adaptation. So we use the same task, but in addition to the standard trials, we added some what we call dummy trials. These frames which are differing 45 degrees from the target. And mixing this with the target elements is expected to reduce adaptation. And these are the learning curves. So here we have 3 measurements every day. And we have 2 conditions, with adaptation and without adaptation. So with adaptation, we get these curves. So we see that 1, 2, 3, day 1, we start learning, and then we get deterioration. Now there are fewer trials here, so compared to the 800, we have only 200. So this is 1 point on the previous study showing adaptation. So adaptation is weaker here, and the stimuli are shorter. So, but we see every day that there is some improvement and then deterioration. Now, once you reduce adaptation, you get these field symbols. So we don't get this deterioration. Performance, the threshold just decrease continuously. This is one effect of adaptation. But more surprisingly, with adaptation, we get the typical specificity. Once we move the target to a new location, performance goes up, but without adaptation, we don't get specificity. Okay, so that's, okay, no time. So we conclude that specificity is the outcome of local spatial temporal adaptive processes. Once removed, enable space invariant learning. So that makes adaptation really as a main suspect for specific learning. Another study, interesting study, is with autism. We did the same study with the autistic subject. And there the finding is, I'll show you some, okay, the data. So what happened with the autistic subject? So again, we have the same, this is with adaptation, the blue symbols, the green symbols are without it. No, this side is with adaptation, this side is without adaptation. The blue symbols are autistic subject, the green symbols are standard, typical subject, non-autistic. So the main finding is that the autistic subjects are highly specific in the standard condition. They are even more specific than standard subject in the sense that they don't learn even in the second day. Most often with normal subject, with standard subject, the second location is much faster, learning at the second location is much faster than the first location. With autistic subject, the learning at the second location is slower, which is very interesting. This somehow goes with typical properties of autism. But once you remove adaptation, then you get generalization for both populations. The autistic subjects have no problem anymore. They now generalize. I mean, these are the blue circles. So this may give some indication for one problem in autism, and that's the failure of adaptation or some problems in the interaction between adaptation and learning, which again, as I said before, can be more general, not necessarily a property of vision. or perception torch. So to summarize, stimuli are mapped. This is the way we think things work here. I mean, that's the way we believe these things can be explained. Stimuli are mapped into some topographic representation, let's say V1, V2 in the visual cortex, which we call early vision. We still call it, even though we know that there are many kind of effects like top-down and attention. Early vision adapts, and there is a higher level readout stage that reads the early representation and classifies the target, let's say vertical, horizontal. There are this brain that learn what's going on in the sensory side and try to figure out, but sensory side always adapts, so it's changing. So there is a game here. There is some kind of a race to identify during adaptation. So generalization depends on the invariance of target representation under the required transformation, and invariance fails when you have local adaptation, because we see the adaptation specific to target, and then once moved in different location, you need to repeat the same process again. Okay, and so final remarks. Sensory adaptation is somewhat more complicated than expected. Task dependent, showing learning and dependence on expectation. We have some more recent studies by Noga Pinchuk-Jacobi and Ron Deckel sitting here, showing that adaptation somehow depends also on the expectation, not only on the current stimulus, but also on what you expect the stimulus to be. And there are probably two effects of adaptation. Negative, reduced saliency. Apparently, one possibility here that adaptation reduces saliency of the texture target. But there are other effects of adaptation that may be positive, because adaptation somehow is expected to serve some useful process. So one idea is that it improves grouping or noise reduction, and which should affect grouping. And overall, it should affect the excitatory inhibitory interaction in these regions. These are the interactions studied by Uri Polat for many years. And probably in autistic subjects, these interactions, or what some people call the EI balance, may depend on the training procedure and stimulus parameters, and etc. Thank you.